In question 1 it says two parallel charged metal plates A and B are in a vacuum. At a particular instant an electron is at point P, so there's an electron there. On the diagram draw field patterns due to the plates. Now when you have parallel plates there's a uniform electric field in between those plates. So the way that you show that is that the electric field lines need to be evenly spaced. There needs to be the same distance between each line. The arrow shows the direction that a positive particle would move. So between parallel plates it would obviously be between the positive and the negative. So you see I'm trying to draw, obviously you'll draw this with a ruler. I'm trying to draw that these are evenly spaced. Now on the edge you get a curved effect. Now that doesn't look very great. I'll try and do a better one on that side. No, not very good. But you get a curved effect on the end. So we got parallel. These should be hitting the plate at 90 degrees. Something like that. And then an arrow to represent the direction of the force on the electron P. So the force on P would be in the other direction because it's going to be attracted towards the positive plate. So it would have something like that. Then it says the acceleration of the electron at P is 8.8 times 10 to the 14 meters per second to the minus 2. Determine the magnitude of the electric field strength at the point P. So we've got the situation here that from this formula over here that E is equal to F over Q. And also I've been given my acceleration, so what does that make us think of? Well, acceleration with force is equal to mass times acceleration. So my electric field strength is going to equal the mass times the acceleration divided by the charge. So we need to put those values in. The mass of an electron is, you need to look that up in your data booklet, so you can put that in there. This is your acceleration, that's there, and your Q is 1.6 times 10 to the negative 19. I'm just going to give it a guess. I think it's about it's a factor of 10 to the negative 31, I think, for the mass, and your acceleration is 8.8 times 10 to the 14. There's some value here, so just check that out. When you multiply that and divide, you get something like 5.0 times 10 to the 3 newtons per coulomb to the minus 1. Then it says the electric potential energy of the electron changes by 1.9 times 10 to the negative 17 joules as it moves from one plate to another. Show that the potential difference between the plates is 120 volts. So remember from this formula here, if I go up here, let me have to close this down, but if I go here I get this formula over here, this VE. This is the energy. It comes from this formula that V is equal to W over Q. That's your definition basically of your potential difference. It's the energy per unit charge. So W is equal to V times Q. So in putting here, we've got an energy there, a W of 1.9 times 10 to the negative 17 joules. We've got our Q is an electron, so we're going to get 1.9 times 10 to the negative 17 is equal to V times Q, which is 1.6 times 10 to the negative 19. So V, when I divide this, divided by 1.6 times 10 to the negative 19, that cancels on that side, I get a value for that of 120 volts. Right, going over the page now, this is actually a regular resistance problem, but we can still do that here. So we have here a resistance R and a filament lamp L are connected in series with the battery. The battery has an EMF of 12 volts and an internal resistance of 4 ohms. And that's important. The potential difference across the filament lamp is 3 volts. So we've got 3 volts across there. And the current in the filament is 0.25. So because this is a series circuit, we know that there's going to be 0.25 amps through the whole circuit. So define the EMF and the concept of internal resistance. Okay, so you need to look at your definitions for this. The EMF is the total energy per unit charge that a cell delivers to the circuit, and it includes the energy given for the internal resistance. So it's the total energy per unit charge that a cell delivers to the whole circuit. And the internal resistance is the energy within the cell. So as the cell is providing energy, it is also having to overcome some resistance within the cell. Then it says calculate the total power supplied by the battery. Now we have an EMF of 12 volts, so that's the total energy per unit charge. So we can go to our formula here that we have P is equal to V times I. So we're going to get 12 times 0.25, and that will give me my power, which is equal to 3 watts. Then it says calculate the power dissipated in the external circuit. So we're going to have the power dissipated in the external circuit will be the total power will be 3 watts minus the power that is going to be lost in the cell itself. Now there's a 4 ohm resistor, so using this formula over here, that power is equal to I squared R. So the power lost in the cell itself is going to be 0.25 squared times 4 ohms, and that will give us our power dissipated in the external circuit. So let me just work that out. So we're going to get 3 minus 0.25 squared times 4. Oh, sorry, I made a mistake in my calculator here. 3 minus 0.25 squared times 4. So I get 2.75. So 2.75 watts. So there is a 0.25 joules per second that is lost within the cell itself. And then it says determine the resistance of the resistor R. Now we know that this over here, this has got a certain potential difference across it. It will have I of 0.25 going through it. Now we can look at the power across the lamp. The power across the lamp is going to be 0.25 times by 3, because it's going to be IV coming from this formula over here. So there I'm going to get 0.75. So the resistance here, the power lost over the resistor, is going to be 2 watts, because you've got 0.75 watts is lost over the lamp. Therefore it must be 2 watts is lost over the resistor. So we can use our formula here again. Power is equal to I squared R to work out the resistance. So we're going to get 2 watts is equal to I squared, so it's 0.25 squared times by R. So obviously I'm going to divide that 2 by that 0.25 squared, so I get R equals from that, and it should be 32 watts. There's a number of different ways of doing that. That's just one of the ways.